As a third example, getting something or moving towards something that's a bit more complicated and maybe even more interesting. Here's a quote-unquote car door example. I had a master's advisee who worked for an automaker. He was a door engineer, and one of the things that he did was to make analyses of how variability in the geometry of part features would affect the overall appearance of a vehicle. So here's a little cartoon of the kind of problem that he worked on. This is actually reasonably close to a real problem here. What we're dealing with here is a car door. So the heavy lines here represent the cartoon of a car door. And we're going to take this heavy line as being the line of a door frame on a car. And if you're going to go buy an automobile, you're interested in seeing that the gaps between the car door and the door frame are uniform. You don't want to see a door that appears to be hanging on the car hanging not straight on the car. Well, you can imagine that there's a variety of things that could affect whether or not these gaps are similar. In particular, there's matters of geometry of the door. So here is, say, this dimension of the door that I've called Y. The size of the door in that dimension. There are these angles that talk about how square, or if it's not meaning to be square, how not square the door is. There's the matter of how far below this corner of the door the door is hinged to the body of the car, and that's a variable that I've called X here. And there's a question of when this door is put on, what kind of an angle is there between this line and a line parallel to this body door frame. All of those geometry kinds of things go in to in a deterministic way into functions that could be used to tell you what G1 and G2 are, gap number 1 and gap number 2 are on this door. And I guess I also want to say that, well, I'm measuring down D units from the hinge for this second gap here. The geometry for writing, the trigonometry required to write that out is not absolutely trivial, but it's possible to do it. And let's see, I've got that on. So there is the picture in the slides for this module, and here's a set of equations. Some of these equations are vector equations, so P and Q are vectors, S is a vector, u is a vector, g1 and g2 are just scalars. The point here is that I could write out a fairly complicated function of all of these features of the door and how it's hung on the car to give you deterministic functions for gap 1 and gap 2 in terms of the other variables. Geometry, trigonometry gives me that. The question then is how much variation in the inputs affects variation in these gaps, affects in particular things like the difference in those gaps, whether the door seems to have the same gap at the top as at the bottom. This is a quote-unquote tolerancing problem, statistical tolerancing problem, probabilistic tolerancing problem, because my students or my advisee, the car door engineer, had to set specifications on these various features of this door. That is, it was his job to say that, well, y should be something plus or minus something. This angle should be something plus or minus something. This dimension x should be some target value plus or minus tolerances, so that at the end of the day the variability seen in gap 1 and gap 2, or the difference, say, between gap 1 and gap 2, is acceptable in terms of what a customer wants when they buy a car from this company.